Good afternoon, everyone. This is Pouya Banibayat from Midas, and welcoming you to our e-learning session. If you remember, in the first session of this series, e-learning courses series, we had Dr. Gerger talking about the network-tied arch bridges. And today, this is a follow-up session on his presentation. And what he explained there, I'm going to have more in-depth discussion here by sharing the case study that he has done and talking about the steps of the design and construction of those type of bridges and whatever consideration requires for an engineer to consider. So if you don't mind, I just quickly go through the e-learning courses and just as a reminder, refreshing your mind, and then we start the presentation. The e-learning courses is a conduct of three. The e-learning courses is composed of 3 sessions: technical seminar, case studies and discussion, and numerical modeling and analysis training. In the first session of technical seminar, we have professional engineering professional engineers coming and talking about the certain project that they have done and sharing the challenges that they faced with other engineers. Then you see a list of presenters that we had, and then, as we discussed last week, Mr. Gerger presented his presentation. The second part of this series will be in-depth case study and discussion, and this is the session that you are attending. In this session, as I said, we're gonna cover the technical seminar topic that, as you know, the last sessions was for the network-tied arch bridges, and today we're going to have more, share more detail about those type of bridges. These are the examples of the different type of bridge which we will be having those in the upcoming sessions. And then finally, we're going to have the numerical modeling and analysis training. So in this session, which is a last session of each series, the attendees will learn how to use the computer programs to model those type of bridges and how to perform different type of analysis to extract the desired results for purpose of the designing that type of bridges. Okay, so today we are talking about the session is about the in-depth case study and discussion, as you see, and then the next week we're gonna have numerical modeling, and the people who attended will be attending the next session will provide them a free trial license. Then they can practice while they are attended in the session, because it's going to be step-by-step modeling, performing the analysis, extracting the result, and then any functions that required for this type of bridges will be shared. Okay, so let's start the session. As you can see from the title, it's in-depth case study and discussion of network-tied arch bridges. So I divided the session into 3 parts. The part 1, we're going to have a case study of the Happy Hollow Park network-tied arch bridge, which was a pedestrian bridge, providing a general information, geometry, dimension, and all. In the second part, we have we're sharing the advantages of network-tied arch bridges compared to the conventional tied arches. And in the last part, we're going to show you the design of the network-tied arch bridges, step-by-step designs, and erection or construction methods, and the considerations of these two which an engineer should take care of during the design, and finally showing the finite element solution for design and construction of network-tied arches. So part 1 is the case study, and I'm going to share some general information. I collected general information about this bridge from Gregor's paper, which was published in the Proceeding of International Bridge Conference, IBC 2012. So the Happy Hollow Park and Zoo opened in 1961, and this project was a part of a renovation for the site in the city of San Jose in California, and they wanted to have a signature bridge for their park, their national park, and initially it seems that there was a cable stay proposed to be built in this area, but because the budget went beyond their, the construction cost went beyond their budget, so they denied that, and after that the Art Network Tide Arch Bridge type of bridge was proposed by HNTB, and it's been accepted because the the cost of total cost of the bridge, I mean the design and construction, was satisfying the owner's requirement. So at the end they come up with two network tide arch bridges, as you can see in this picture. The lengths, the spans are 270 each, and totally it comes up with 540. This is a plan view of the bridge, and you see the configurations. So the bridge is made of the arch itself is a circular arch with a radius of 225 feet, and the basket handle configuration arrangement is selected, and as you can see, the springs line, distances between springs line are 13 feet, each these two, and totally 88 inclined hangars is used, and as you can see, the angles from 57 degrees to 71 degrees is increasing gradually in both sides. And as you see, the design load was a pedestrian traffic plus a 5-ton maintenance vehicle. As we discussed, these bridges are pedestrian bridges, so this is the load that we're going to apply on them. So erection of east span over the Coyote Creek pedestrian presented a particular challenges. So technically, the that zoo didn't let the constructor to use a false works. Therefore, the constructor has to use a cable state false work to complete the analysis. So you can see just briefly see the erection sequences, but we're going to talk more about this in detail, that why this type of false work is used and what's the advantages of it, and then what we have to consider in this case. And the red dots that you see on each hanger or the temporary cables are the forces or stressing forces that applied on the cables to keep them in place and help us for during the construction. So you see some diagrams of the displacement diagrams of the bridge during the construction. So later on I will explain that during the construction how was the behavior of the structure, was it non-linear, and what we have to consider there. And as you can see, during the construction, each time we are just applying the different stresses on different hangars, and definitely by applying stresses we have different deformation of the bridge, and then finally the bridge comes up with the final geometry and final shape that it has to have. So this is a video I prepared, so you can see how the construction is done. As you can see, as I said, this is like a red dot showing the stresses that we applied on different hangars or the cables that we use, the temporary cables. All right. So after the structure is completed and the hangars are placed, now the hangars are stressed, and then is the time to remove the temporary supports. Okay, so you're gonna see the removal of the temporary supports, and then it's gonna be the bridge itself. And after that, when we removed all those temporary supports, now is the time to adjust the the hangars, and then we're gonna I will let you know that what functions is used to come up with the those force arrangement, and then cable tuning. All right, so I just skipped at this, just showing how this cable tuning happened to come up with the final stage of the structure. Okay, so let's move to part 2. Part 2 is the part that we're going to talk about the advantages of network tied arches, and then having a general comparison between network tied arches and conventional tied arches. Okay, so in these diagrams you see a tied arch bridge with vertical hangars, as you see in the top, and in the bottom you see the network tied arches. Based on the definition, Mr. Tevet, which is the father of network tied arch bridges, defines that network tied arch bridges are a type of bridge which the hangars are intersecting with at least 2 other hangars. So this intersection may be more, is completely based on the configuration and then the dimension of the bridge. By the way, I have to mention that I got a lot of information from the from the technical papers and other sources available on the website www.network-arch.com, as you see written here. This site is for Mr. Tevet, and it has information about almost all network tied arch bridges all over the world. And if you are interested, you can go there and get very useful information about this type of bridges. So I'm gonna use some of those. I summarize some of those information in this presentation. I'm gonna share it with you. Okay, so talking about the advantages of network tied arches, let's see what's the characteristic of these types of bridges. So network tied arches are recommended for spans between 250 and 1,000 feet. So it would be very valuable and economical to get the experience with network arches with spans between 400 and 600 feet. So the 400 and 600 feet is like the best size for the spans that this type of bridge could be very beneficial and economical. The inclined hanger with multiple, intersection in tied arches can distribute forces in such a way that bending moment and the shear forces are distributed to the upper chord, which is arch, and then the lower chord, which is tie, just like a truss. So comparing these two, so you see this network tied arch is more similar to the truss structures, although these are just hangers and then tensile elements. The behavior from this and the behavior are different from the truss element, but it looks more similar to those type of bridges. And this configuration gives actually a higher stiffness to the structure, increases the redundancy, and therefore it improves the behavior of this type compared to the conventional type. We discussed that this inclined hanger makes a better distribution of the moment and shear, and then this structure is like a stiffer structure, and because of the more redundancy that they have. And also, if these bridges are designed correctly, or in the best way, they can also save up to 45% of total cost compared to conventional type arches, which is a pretty huge saving. So let's zoom in here and then talk more about the stiffness and then the characteristic of that network tied arches. All right, I got these slides, these two shapes from the presentation of Dr. Wallman, because he already presented these to you, and I would just want to have a flashback to what he mentioned. So let me just compare these two. We have two diagrams showing the maximum deflections of these two type of bridges under the same loading. So as you may know, the arch bridges behave pretty well when the entire span is loaded, or you have like a continuous distributed load all over the span, because the hangars are working pretty well, and then the forces go to the arches and then the ribs, and then they go to the support, and everything is fine. But they have problem when they are loaded partially. So partially, I mean, then for example, in this diagram, only half of the span is loaded, so it causes like a more deformation. So comparing these two, they are under the same load, but you see that the maximum displacement under the conventional type of tied arches is 36 inch, while the network tied arch with the same design and the same span and the same load, it comes to 3.3, which is almost 10% of the other one, which is pretty well. And comparing to the conventional tied arches, the network tied arches, the cores are only subject to the smaller bending. So I got these slides also from Gregor's presentation, just in case to having a refreshing your mind. So here what I have two diagrams for the tied arches with the vertical hangers, and two for the network tied arches. So comparing these two, when we have the that partial forcing or loading, imagine that just a half of the structure is loaded. Now you see the distribution of the moment in the tied and also in the arch. So you see how high is the bending moment compared to the corresponding network tied arches. And if compare the lower diagram showing that if we have some losses in the tie, so imagine some part of the tie is not working properly, and we are kind of like losing that part of the structure. So what happens is that the load is here, and then definitely the load should be redistributed to the other part of the structure, and the same with the moment. So you see, if you are losing this part of the arch, of the tie, the bending moment on the arch is increasing suddenly, and you see it's almost twice. And definitely the bending moment in the tie is decreasing. While comparing this type to the network tied arch, you see that when we are losing some element in the tie, what happens is that definitely the moment here decreases, but the amount of moment in the arch is not increasing that much, which shows that the structure behaves pretty well. And then even if something unexpected happens to the structure, or we are losing any structural element, structure itself is smart enough to redistribute the moment pretty smoothly and then behave pretty well. So you see that in this case also network tied arches are behaving way better than the conventional type of bridges. More on advantages of tight arches. They are not sensitive to uneven settlement in the foundations, again because of their stiffness and then the more redundancy. And also their higher strength and low weight give the network tied arches a good resistance for the earthquake. So they behave pretty well for the under the seismic forces. Okay. Now we had an introduction about the project, shared the case study. We talked about the advantages of this type of bridge network tied arches, and then why one, an engineer should select such type of bridge. And now in the third part, I'm going to share some idea about the design of network tied arches, erection or construction of construction methods, and then the consideration, design and erection consideration that you have to take care of, and finally showing you some finite element solution for design and construction. So what I do, I just combine the design and erection together, and then show you in which stage you need to do what type of analysis, what type of result do you need for the design of that part of, that stage of the construction. Okay, so for the design of network tied arches, I divide them into two general stages. One is construction stage and one is final stage. So the construction stage and final, the structure behaves completely differently, and then we have to consider different factors. So in general, all structural components must be designed. Like arrangement of the hangars, we have to find the optimal arrangement. Arches, we have to design them for example, buckling. Hangars, we have to check them for tensile loads and all. Then we have the lower chord or the tied, which we have to check them for the post-tensioning or pre-stressing, using those panels or the trusses that we are using. So differences between the construction stage and final stage, let's just, I listed some of those here, so let's just discuss about them. During the construction stages, actually the structure is not stable enough to self-support itself because the elements that we use are pretty slender and there is no support. So network tied arches, general tied arch bridges or network tied arches are kind of suspension bridges, because what we have is only two supports. If I show you, we have two supports, and then in between we don't have any piers. So entire the force should go transfer to these ribs, and then from the arch goes to the supports, and then transfers to the ground. Okay, so because during the construction we have only those two supports, therefore there is not enough stability for the structure to take care of itself. So we have to be worried about that part. Then there is where we see nonlinear behavior of cables during construction stages, because when you have those hangars, the hangars are not completely tight, because the weight of these tie is not that much, and then also you have temporary supports, so some weight of the self weight of those tie goes to the support. So the cables or the hangars are not really working well during the construction. Therefore, we are seeing that nonlinear behavior, and by nonlinear behavior I mean we are seeing that there's some sags in those cables. Then we see the wind effect during the construction. As I said, because during construction structure is not stable enough, we have to consider the such other loads like a wind on the structure. Then the temporary supports are important. So I'm gonna explain this more, because this case was a special case. We use the they use the cable stays for these supports, and then we have to know the pre-stressing forces in those cables for different part of the construction. Then we have the final stage. In the final stage, actually structure is behaving completely different from the construction stages. So what happens after the arches are placed? Now we have to calculate the forces inside the cables. I mean the stressing forces inside the cables. If you remember on that video that I showed you, after the temporary supports are removed, now we have to do the cable tuning to come up with the final geometry and all. So another thing that we are seeing in the final stage is the linear behavior of elements. So the concrete, if you use the concrete for a slab, now the concrete is set and then it's behaving linearly. If the we use the cables for the hangars, and now they are pretty tight and they are working completely and they are straight, and then they are also linear. So the behavior is changing, although it becomes linear and it's easier to do the analysis, but we have to consider other effects as well. Then we have to consider the critical live load on the structure. So in this case that I showed you for the Happy Hollow Park and Zoo, this is a pedestrian bridge. So definitely we don't have a moving load on that. It's just a pedestrian force and also the 5 tons maintenance vehicle. That's all. But if you have a highway bridge, definitely we have to consider the truck loads and all. So we have to find out the partially loaded or the critical load of that bridge, which causes the maximum effect, I mean displacement or whatever. Also in the final stage, one important thing is we have to consider the extraordinary loads. So by extraordinary loads, I mean something like accidental hanger loss. Entirely, let me show you this. Entirely, this structure is highly, based on these hangers. So if you are losing the hangers, there is no stiffness in the structure, and the structure will collapse instantly. So this is very important to check what happens if one or two hangers are losing, or something happens and they are gone. And then we have to see how the structure behaves and what will the maximum displacement, distribution, and then the safety of the structure itself. Okay. So beside the design, now let's talk about some erection of network tied arches. In general, I can say there are two general type of erections. One is fabrication, fabrication on shore, and then bringing the structure in place and then jack them or pull them and place them in the right location. Another one is using a false works. So using the false work, there are different methods. One is just using a regular fixed false works. Another one is a cable stays. So this is the first method, that the bridge itself is constructed on shore, which is way easier, and you need less equipment to build the structure, and then they're gonna bring it in a location and then using a jacks or just pulling it up and then place it in a location, put them on the supports, fix them, and the bridge is ready to be open to the traffic, as you see here. And then because one advantage of these structures is that network tied compared to the span length is very, very light, and then it's very easy to pull them up or just use the jacks to place them. This is another method. This slides showing you how that you now using the false work happens. So if this is the free span that we have to put the bridge, so you can use the temporary supports and you now build the arch you know, by placing them, and so arch, and then the ties are created, constructed, and then we applying these hangars, and then fix the hangars, and then placing the here they used some pre-stress panels, and then you know it's ready to carry the load. This is another example. So this one we had the fixed false works. Here we use the, you see that they are using a cable stays. So this actually is different from what they used in the HNTB used, but they are pretty similar in terms of like a functionality. So here you see that there's just two main towers, and then the hangars are holding these different part of the arch, and when they are meeting each other, so that we can just release those hangars. But this is what happens in the Happy Hollow Park network, network tied arch. So because the you know, the city of the San Jose didn't let them to use false works in this area, so they had to use this temporary tower here, and then using the cables to hold the entire structure. So as they you know, going further for constructing, for erecting the different part of arch and also the tie, so they are using these frames which they are held by this main frame here, and you know, they are placing the arches on top of each other, and then when it's constructed, so they can simply remove these and then install those hangars, and then remove all these. So you saw the construction stage in the video that I shared with you. Okay. So let's, I shared with you that what type of design we have to consider, and then what type of construction do we have. Now let's combine those two and see how we have to use some finite element tools to help us for design of this type of bridges. So the first part, I'm going to focus on the design for the construction stages. As we discussed, the stability is an issue because the elements are slender, and then we have to consider those. Then another thing is we have to provide required stress in the cable during arches and you know, tie direction. For example, if you look at this, if we you know, if we just pre-stress these cable right here, the last cable, okay, this support remain horizontal, but imagine if we apply this, added this rib here, and added more of the tie here. So what happens, we're going to have some downward deflection, and therefore the structure will not remain straight. Therefore we have to apply more pre-stressing force on the cable to bring it up, and then the final stage it comes completely horizontal. So this actually called lack of force, lack of fit force, which you need additional pre-stressing force inside the cable to make sure that the final stage will become completely horizontal by applying these stresses. Okay, and then this, you see nonlinear behavior of the structure and also cables, which you can see here. When we have that additional displacement, when we come up with the large displacement, then we cannot consider them as a, you know, assume that they are linear. So it will become nonlinear geometry, and definitely you have to run a, if you're doing the analysis with any software, definitely you have to run a nonlinear geometry nonlinearity analysis. So the lack of fit force, this is also one function that Midas will provide you, and it could be very helpful during the construction, because as I said, if you are not coming up, for example, you are constructing this from left, this one from right, and then you assume that these two should meet each other in the same location. So if the structure is not horizontal, or they are going different directions, that's why what happens to causes more money you have to spend to fix these, and other stories. So this lack of fit force is a function is just help a lot in case of like finding the required stresses during the construction stages. Another issue that we are seeing here is that hangars itself are not straight during the construction. So the construction stages will be, we have the ties, which is a lower chord, and then we have the arch, which is the upper chord, and then we are just placing these hangars. So during this stage, we are not seeing, we are seeing the nonlinear behavior of hangars themselves. So we have to use a nonlinear element. So one element that Midas will provide to for this type of structures is a cable. Cable is a nonlinear element, and then you can use it for the geometry nonlinearities. Completely give you those sags and all those, which is pretty helpful, and makes it possible for the engineer to have a real understanding of the structure, and then see how the structure is gonna behave in the during the construction. Another thing that you need to consider during the construction stage is the time-dependent material property. So time-dependent material, I mean the creep and shrinkage, and also compressive strength of concrete. So we can consider these two. You see one diagram here showing a creep coefficient of concrete, and you see the kind of similar type of curve for the compressive strength of concrete. So it depends on the loads that you apply, depends on the size of the element that you using. So this causes a different losses, different forces on your structure, and different deformation. So definitely you need to use such a behavior, or time-dependent behavior. And Midas will also provides you this based on a code, and also based on the user-defined functions. In the next session, we're gonna have in detail, we're gonna show you how you can set these up, and then how you can use them in the real design. Then another thing is using a composite section, because for your deck you may need to use a composite section. And then composite section, as you know, it could be a steel eye girder with the concrete on top, which they are working together, and then considered as a composite. Midas will provide you such a section, and then you can, for example, tell the software that this concrete will be set after 3 days, and after 3 days they work together as a composite section. So these are two functions that can help the bridge engineer to design the network tied arches. So let's finish this and switch to the design for the final stage. In the final stage, as we discussed, we are seeing completely different behavior of the structure. We see the cables are behaving linearly, material are set, concrete is set, and then we are not seeing that much of time-dependent material behavior. And other than that, hanger force adjustment is required because if you remember, here we discussed that during the construction stage we need some additional forces on the cables, for the cables of the temporary support, to come up with the final geometry. Now the structure is set, is completed. We applied these hangars. Now we have to apply the pre-stressing on the structure, on these cables, to form the final shape of the structure, and it's ready for carrying the load on top of it. So for that one, we need to do the hanger force adjustment, and that's an optimization problem with a high number of parameters. For example, in case of Happy Hollow Park network tight arches, there were 88 hangars, which causes it makes a very large matrix of 264 by 264 matrix for doing the optimization on that, and then coming up with the best forces in each hanger to come up with the final geometry, which is time taking, and doing one single mistake, so it causes every other forces. And then you need to consider the moving load analysis. As we discussed, we have to find the critical loads to see what's causing the maximum effect on the structure. It could be displacement, or it could be forces or moments. Then also we need to consider the extraordinary loads. So let's see how we can do those. So the first one will be hanger force adjustment. So the hanger force adjustment, as I said, structure is completed, those supports are removed. Now we have the hangers, which have some pre-stressing force or stresses. Now we have to apply some more forces to generate the final geometry. So using this hand calculation or using the spreadsheet may be a very time consuming and then very sensitive. While you can use Midas Civil, Midas Civil provides you those matrices, which we call like influence matrix, and then this function, which is called unknown load factors, would provide you those functions, and just make it so easy for the engineer to come up with the final forces in one shot. Another thing is cable tuning, which this is another function for the structure, which for example, after this hanger force adjustment, for example, the software provides you that the force in this element should be 205 kips. So now you can't apply 205 and want to see what happens if you apply 200, and then what's the effect on the other structure. So you can manually play with those forces and then set them in the in the range that you want, and then ask the software that you don't want to, for example, bending moment of certain element on the tie or on the arch goes beyond a certain value. So the software will provide you, adjust the forces based on what you exactly want. All right, how to find the critical forces? So it depends on the width of that bridge. It might become more complex. But if you have one or two lanes, so it probably is easy to do the hand calculation. But you have a wider bridge, and then you have a couple of vehicles running at the same time. So you may not be able to find the critical force for every single element of the arch, and also for the tie. So you need to use a software for finding those functions. So as you see in this diagram, Midas Civil, after you're running the moving load analysis, for example, if you are interested to know what is the maximum bending moment happened in this girder, in this exterior girder, you can select this exterior girder, and the software show you what load cases or what arrangement of the structure, the moving load causes the maximum bending moment in this element. As you see, this is a truck, and then this is the distributed load or lane load on the structure in a different location. So this makes it so easy for you to find that critical load. And also you can save those load as a static load, and if you want to do any changes to the sectional property, or changing the that cables or arches, that makes it so easy for the user to quickly check it, because it will be a static load and then it's run in a couple of seconds. And then finally, one of the extraordinary loads to be checked is a hanger loss. If you remember, Dr. Wallman talking about the hanger loss, and he showed you this diagram in a way that when we are losing one hangars, what happens is that we are losing one hanger, definitely, which will be a static load, and the load will be distributed and handled with the adjacent element. But that's not the only effect. We have also a dynamic effect on the structure, because the hangars have pretty high stress in them, and then if you are losing we are losing one of those, we're gonna have an extra forces in the reverse direction, as you see the flash is showing them here, and then we have to consider that dynamic effect. So how to consider that dynamic effect? You can simply apply a static load and then apply some amplification factor, or if you want to see the real behavior of a structure, you better do the time history analysis. So doing the time history, I prepared this video, and this is also Gregor also showed this to you. As you see on the left bottom corner, you see the time history forcing function, and as you see, the one of the hangars here are lost. And by the way, there are hangars in this side of the structure also, but we just deactivate them, just not to show them, just to see the behavior of structure in that end. So if I play that, you see when we have this hanger loss and we have these additional forces here, which apply dynamically, structure behaves pretty well. By the way, these displacement that you see here are pretty exaggerated. We just show them for the that's just make more sense for the user. So you see, while we are losing one of the hangars, structure still behaves pretty well, and then the force distribution is handled very well, and then structure is still alive and is not collapsed. Okay, so that's what I want to share with you today. So if I come up with the summary, we saw that different type of construction of this type of bridge, network tied arches. We saw the consideration of design consideration in two stages. One was during the construction stage, one was the final stage. And we saw what tools do we need to consider those type of analysis, or apply those type of analysis, or study the structure during those type of stages. And I showed you some functions of Midas Civil which can help you in that way. And then the next session we're going to show you how you can model this type of bridges, network tied arches, from scratch, step by step, and then all the considerations that we discussed now, we're going to see them on the structure. And as you may receive the invitations, we have upcoming technical seminars in the month of March. And please mark your calendar and join us in these sessions. These are also a series, and then after each session we're going to have follow-up sessions, in-depth discussion on the case studies, and also having the training on the modeling, and then finite element modeling. Thank you so much for attending this session. This is my contact information. If you have any questions, please feel free to contact me. And we will share this video, we will upload it on our website, and we're gonna share it with you guys. Thank you so much and have a great day.